Okay, we'll get started now. Thank you everybody for coming. So welcome again. My name is Paul Scotchless. Some of you might know me, but I've been in the industry for about 25 years, working on everything to do with PCPs. I've been with PCM for a little more than 2 years now as the artificial lift product champion here. So I'm going to be giving the presentation today about PCP rod string fatigue. So I'm just going to go back to the presentation here. So just a little bit of housekeeping, I guess. Questions will come at the end of the session, and to ask a question, you type it into the Q&A panel, which you should have on your screens. So you type the question in, and then at the end of my presentation, I will go through and answer those. Now, when we do these presentations in Microsoft Teams live events like this, by the end of the presentation, we get a bit of a time delay. So it starts with 0 delay at the beginning, but by the end of the presentation, we'll probably have about 2 or 3 minutes of time delay. So that means that at the end of the presentation, when I say, are there any questions? I might have said that when you hear it, I might have said it a couple of minutes earlier. So if you have questions during the presentation, please type them in right away. So that way, when we get to the end, there'll be some questions for me to answer. And don't wait until the last minute during the Q&A session at the end to type your question in, because if you wait till the last minute, I might not see it before I end the presentation. So just to be aware of that. Okay, getting into the presentation, PCP rod string fatigue. So we're talking about the fatigue life of the rods in the PCP application. We're not talking about the rotors here. Rotors can have fatigue failures too. We're not talking about those today. And we're also not talking about rods in beam pumping applications. They also have fatigue problems, but it's very different. The solutions are different. So if we're only talking about the PCP application here. The other thing we're not talking about is connection failures. Connection failures is not typically fatigue. If you've got stripped threads or broken pins or broken couplings, that's a different problem, which I talked about actually in my first webinar a couple of years ago now. So I'm going to just put the link to a YouTube video for that on your screens there. If you're interested in connection failures, that's the place to go, and we can talk more about it there. If you have any questions about it, of course, you can go ahead and contact me. So just a quick outline of some of the things we'll talk about. What is it? Some of the randomness, the factors that affect it, effective corrosion. I'm going to talk a lot about this bending stress and the concentration of curvature. That's a very important thing, and most of the things that we can do to improve our fatigue life are based on reducing that effect. So what is fatigue? Fatigue happens in metals in particular. It can happen in other things as well, but what we're talking about is in metal, where when it's subjected to many cycles, tiny cracks start growing in the material, and during each cycle the crack grows, and eventually the crack gets big enough that the remaining material is no longer strong enough to carry the load, and the part breaks, in this case the sucker rods. Cracks tend to start growing from imperfections in the material. There are always imperfections in a material. It's not a manufacturing defect. It's a nature of every material that there's going to be little imperfections in there. We'll talk a little bit more about that in a minute. But the cracks only grow when the load changes. So when there's a cycle in the load, when it goes up and down. There's a whole bunch of things that affect it that we'll talk about. In a PCP application, the most significant form of the cyclic load is the bending. So when you've got your rod running through a curvature in the well, as you rotate the rod, one side of the curvature, or one side of the well, goes from being on the inside of the curve to the outside and then back to the inside. So it's going from a tension to a compression back to a tension. So that's causing a cycle. That bending load is generally very small in a PCP application. Typically about 2% of the total stress on the rod is the bending stress. In a really extreme case, it might get as high as 10%. So it's small compared to the stress that's from the torque and axial load on the rod, but over millions of cycles that can lead to fatigue failures. There's also cycles that are due to slugging, for example. if you get gas, slugs of gas or slugs of solid going through, you get spikes in the torque. If those are happening frequently, then that's also going to be causing or making the fatigue problems a bit worse. Those are generally only a problem if you've already got a fatigue problem from being in a deviated well, or if your torque is very, very high, or your overall stress in the rod is very high. If you're operating very close to the yield stress, then those slugging events can take that stress above the yield, and that will lead to early fatigue failures as well. Just some pictures. This picture on the top left here is a good example of a classical fatigue failure. And what we see here, there's two distinct regions. The first one is very smooth. That's where the crack was growing. So this is where eventually where a crack was forming, and it grew this big. You can see the line where it got to, and at this point, the remaining material was no longer strong enough to carry the load, and it broke. And that final fracture is the rough surface. Going down below it here the smooth surface is very, very large. In the analysis we did for this well, it showed that the rod was only at about 12% of its capacity. So that's why you can see that there's only about 12% of the rod left that had the final failure on this rough surface here. The location of a fatigue failure is shown on these other. What's on this picture here too? You can see there's the upset is right here. The upset is right here. This isn't some kind of narrowing due to tension. This is the shape of the rod at the upset. We have the wrench flats. We've got this is called the bead, and then there's a transition down to the rod diameter. And in these two examples, the rod has failed right at the end of that transition, where it's right at the rod where the rod has reached its nominal diameter. And that's very typically, and again in this third case over here, that is very typically where you see a fatigue failure. In fact, I will go so far as to say if you see a fatigue failure somewhere else on your rod that's not either right here or within a few inches of this spot, that rod was damaged before it went into the well. It could have been bent, or there could have been a big nick in it or something like that. But it's just extremely unlikely you're going to see a fatigue failure naturally occur somewhere else in the rod other than this point. And I'll talk about why that is in a minute. Just a little bit about fatigue in general. This is an example. At the top left here, we have a very simple fatigue testing apparatus. So they've got a specimen that's attached to a motor with a load hanging off of the end of it, and the bearing is there so the load can hang down as the specimen rotates. You rotate it for a few million revolutions until it breaks under this load. So there's no axial load, there's no torque on this. It's only bending stresses from this load hanging off of it, and that's what's being measured on these. And the results are plotted in a graph like this. On the vertical axis, we have stress, which is S. So high stress is this one here is stress divided by the ultimate stress, but it's just a measure of stress. And then on the x-axis or horizontal axis, we have N, which is the number of cycles. So this is called an SN curve. So each of these dots represents a test on this apparatus where they loaded the specimen to a certain with a certain weight to put that stress in it, and then ran it until it failed. And you can see there's a large amount of randomness here. So for example, at 0.6 or 60% of ultimate, we've got the first failures are happening around 100,000 cycles, and we go over here and there's some failures that 10 million cycles, or there's some specimens that lasted 10 million cycles without failing. So there's more than 2 orders of magnitude of difference between the first failure and some that haven't even failed yet. So we can't predict exactly when a failure is going to happen, but if we use this black line, which is drawn on the left side of this cloud of points, then we can get a good estimate of what the earliest possible time to failure is. Now, the other thing to take note here is, again, there's no torque, no axial load. This is just pure bending in this. Well, it's not pure bending, there's some shear as well, but it's basically just a bending load. So all the stress is alternating. This is very different from our PCP application, where we've got our torque and our axial load are very constant. They're a very high stress, but they're very constant. And we have a very small alternating stress. So we can't use this result directly. I once had somebody ask me, they said, well, our rods are loaded at 70% of the ultimate strength. Shouldn't this graph tell me that it's only going to last for 20,000 cycles, which is a few minutes? and he was misunderstanding. You know, that 70% of the stress in our PCP application, that's a constant stress. It's not an alternating stress. The alternating stress is much lower. So there's some formulas you can use to convert your high mean stress and low alternating stress into something you can use to look at this graph. I'm not going to talk about that today, but there's a reference in the back. You can look it up if you like. Okay. Some factors that affect the fatigue life in no particular order. Torque and tension, these obviously affect the total load on the rod, the mean stress on the rod, along with the rod diameter. The coupling and centralizer diameter certainly has an effect on the concentration and curvature of the connections, and we'll talk more about that later. Wellbore curvature, of course, the straighter the weld, the less of a problem fatigue is. The more deviated, the more of a problem. Distance between upsets affects that curvature concentration, so I'll talk about that as well. Material properties, this basically refers to that SN curve. Every material will have its own SN curve, and that obviously, you know, how high that graph is, you know, high stress, and you like to have a very small slope on it, so it goes out to very high cycles. That would be good, but every material is different. Corrosion affects fatigue. I'll have an example of that in a minute. And then new versus used rod. New rods shouldn't have any fatigue cracks in them. Used rods, whatever cracks were there from the previous installation are still there. And if that rod goes back into the same place or somewhere in the well where it's even higher bending stresses, then it's going to fail very soon, because the cycle count doesn't reset to 0 just because you did a workover. It continues from where it left off. On the bright side, often the rods don't go back in the same place. So if you have a rod that had some significant fatigue cracks, if that rod happens to be placed in a straight section of the well on the second run, maybe you get some better life out of it, but you can't guarantee that, of course. So we'll talk more about that in a minute. Just looking at these in some groups. So mean stress, very important, of course, the torque, the tension, the rod diameter. The alternating stress, that's the bending stress in the rod, affected by the diameter and that effective curvature. Material properties, so the SN curve basically, and the surface properties as well. So one thing I'll mention there is that most sucker rods that you'll buy, other than polished rods, are hot rolled. So it's a process in the manufacturing process they used to make them. That leaves a certain surface finish, which will have its own likelihood of causing fatigue problems or its own effect on the fatigue. If you were to polish your rods, of course, you'd remove a lot of the surface imperfections and you get better fatigue life, but nobody's going to run a whole string of polished rod. That would just be too expensive. But what is a surface property that is relevant here is most sucker rods, the manufacturers use a process called shot peening. After they manufacture the rods, it goes through this process which puts in some residual stress in the surface, and that is supposed to improve fatigue life as well. It's particularly designed for the beam pumping applications, but it's likely to improve the fatigue life for the PCP applications as well. If there's any corrosion that will affect the fatigue life, I'll talk about that on the next slide. And then, like as I said, used rods. Ideally, you're doing a non-destructive testing method that's looking for fatigue cracks. You cannot see fatigue cracks with the naked eye. So when you're doing a visual inspection of rods, obviously, if you see anything that's got corrosion pits or visible wear or any kind of visible damage, you're going to not reuse those rods. But you can't see the fatigue cracks with your eye, so you need to use a different testing method to find those if you have that capability. Tracking the run life of rods is difficult, of course. They don't have serial numbers on them, so they're much harder to track. But for a string that goes into a well, you know how many cycles it had in that installation, but then it goes into another installation, it's much harder to keep track of it. So just for corrosion here, I want to talk about this a little bit. So this is a set of SN curves for a particular material, and they've done 3 tests here. The first test was in dry air. You can see the basic shape of the SN curve based on the dots they've got. These ones over here, these lower stresses, they never failed. So it's quite common in steel when there's no corrosion involved and when the loading is fairly simple, like just pure bending, that if you keep the stress below a certain limit, you'll never get a fatigue failure. So in this case, we're seeing that at about 155 KSI. If we keep the stress below that, it could last forever in that particular application. As soon as you get corrosion involved, now we don't see that anymore. So the second line, this is just in moist air with 93% humidity. So you're in a tropical climate or something like that. And here you can see there's a much steeper curve on it here. We do have a couple of points here that have got to 10 million cycles. If you're below about 112 KSI, it hasn't failed yet, but with the presence of corrosion, that doesn't mean it's going to last forever. It just hasn't failed in 10 million cycles. And in a PCP application, if you're running at 200 RPM, for example, 10 million cycles is about a month. So just because it hasn't failed in 10 million doesn't mean it's not going to fail. Because you do have, even if you've got a fairly benign environment with, there's water in your wells, in most wells, a little bit of CO2 perhaps, you're going to have some corrosion. So it's likely this is not an endurance limit we're seeing here, but just we haven't reached failure yet. Our third line here is now in a salt solution of water with some air in it, and you can see again the curve is steeper again. So corrosion speeds up the fatigue, makes it happen faster, and it makes it so there is no endurance limit anymore. So just so we're aware of that. And again, this is an SN curve that's for fully alternating loads. It's not the same as what we see in their PCP application. We need to do a conversion to make that work. So the bending stress, this is what's happening each rotation of the rod as it goes from tension to compression and back. The bending stress is a function of the rod size, so the diameter, the curvature of the well, and also the material property. Now with steel, all the different grades of steel have approximately the same Young's modulus or modulus of elasticity. So really that's not going to have any effect on when you're choosing different rods. So it's the diameter and the curvature. Now the problem is that the dogleg severity in your well, you've got a survey, it tells you what that is. But it's not evenly distributed along the rod. Even if the curvature in the well is smooth, in the rod it's not. And I'll show you that in a minute here. So we need to calculate what is the maximum curvature in the rod. And it's near the connections. That's why the failure happens there. So as an example here, if you've got 1-inch rods with full-size couplings and a 5-degree dogleg with about 20,000 newtons, that's about 4,500 pounds of load, which is a moderate load for a 1-inch rod. The effective curvature that's only just for a couple of inches near the coupling is over 30 degrees per 30 meters. So it says 30 degrees per 30 meters because that's how we measure it, but it's actually only over a couple of inches. And you get this really increased curvature there, and that's why we have fatigue failures in those locations. That curvature is going to increase as we have higher tension, as we have a bigger upset between the rod diameter and the coupling diameter. That's really the main cause of this is that upset. And as we have a longer space between them. Now, our rods are 25 or 30 feet. We're not going to make that longer. But if you make it shorter by using rod guides, for example, or if you run pony rods, then you actually will decrease that effective curvature and improve your fatigue life. So we'll talk about that again in a minute. Going to this slide here, this is showing one rod length. So we have 7.6 meters, 25 feet of rod. The blue line represents the tubing in a 5-degree dogleg, so 5 degrees per 30 meters. And just to look at the scales here, we've got 25 feet along, or 7.6 meters along the x-axis here. Our y-axis, this tubing is offset by a little bit more than 2 centimeters, less than an inch. So over 25 feet, the middle of the rod is offset by, or the tubing is offset by less than an inch. That's a 5-degree dogleg. It's actually quite a small curvature when you look at it. The orange line represents the surface of the rod. It's offset at each end by the size of the coupling. So in a full-size coupling on a 1-inch rod, will offset the rod by about 15 millimeters from the tubing wall. So that's what we have here. At each end where the couplings are, it's parallel to the tubing wall, and it stays parallel. It doesn't matter what happens, it's staying parallel. Unless, of course, you've got big changes in wellbore curvature. But if you have a section of the well where the curvature is consistent, you got several rods going through that, those couplings are going to be parallel to the wall. And they're going to stay that way. As we put tension on the rod tries to take the shortest path between the couplings. So the more tension you put on it, the more it's likely to try and take that shortest path. And what's happening there is that it's concentrating the curvature. So we're seeing here just the first 50 centimeters or so. You can see it stays parallel on the right at the coupling. The more tension there is in the rods, the more it's concentrating all that curvature in this one spot right near the coupling. So this is why we see fatigue failures at the coupling, and it really affects the things we can do to improve our fatigue life. We want to reduce this concentration of curvature at the coupling. So what are the things we can do to improve our fatigue life and reduce this concentration? First thing is to drill smoother wells. It always amazes me how drillers are rewarded for saving a little bit of money when they're drilling a well, even though that results in the production operations over many years having to spend much more money. It's not a good economic decision, but it happens all the time. So they save $200,000 by drilling a well quickly, and it costs the production team millions through the life of the well, and perhaps even reduces the overall economic recovery of the well. So drilling smoother wells is definitely something you want to do. I know most of you listening probably have no way of controlling that. You're dealing with the wells that you've got. But if you're ever have a chance to have some impact on the drilling plans and drilling procedures, keeping those wells smooth is the best thing to do. Reduce the amount of curvature. So you've got the well that you've been given with whatever its curvature is. What's next? Continuous rod is the first option. With continuous rod, you have no upsets other than at the two ends of the rod. So the rod simply follows the tubing. Whatever the tubing curvature is, the rod will have the same curvature. So that will give you the very good fatigue life. I'm not saying you'll never have fatigue failures with continuous rod, but when it does happen, there's usually when there's significant corrosion involved. By itself, it's usually very good. The next step, if you can't use continuous rod, make sure you're using the smallest diameter couplings you can. Use slim hole couplings. I always recommend slim hole couplings, but I do recommend using high strength slim hole couplings to make sure you're not losing any torque capacity there. If you're using rods that are specifically made for PCP applications, the drive rods, or they have different names depending on who you're buying them from, they often come with a reduced pin size. So for example, you can buy 1-inch rods with 7/8 inch pins on the end. So now you can use a 7/8 slim hole coupling on there, and you get a much reduced upset compared to a 1-inch full size coupling with the rod being the same. That's a very effective product that's been used for a long time in Canada. But even if you're buying other sizes of rod, for example, 1.25" rods or 1.5" rods, there is no 1.25" or 1.5" couplings out there. So those rods all have couplings that are no bigger than 1 1/8. So 1.5" rods typically have 1 1/8 inch connections on them. So it's already a reduced. 1.25" rods can come with 1-inch connections or 1 1/8. So obviously 1-inch connections, they might not have as high a torque capacity, but if you make them up properly, they're still as strong as the rod body. So using that, you get a smaller diameter connection. Always a good idea to keep that connection small. Next step is to reduce spacing between the upsets. So you can either put pony rods in, put some 10-foot rods through that section, so your couplings are every 10 feet instead of every 25 feet. That can go a long way. That means you're making up a lot more connections, of course. So the other option is to use rod guides. I would recommend molded on rod guides and not the snap-ons. It's very important that they stay in position. Snap-on guides tend to slide along the rod, and often you'll do a workover if snap-on guides have been used, and you'll see that wherever it was installed, you might have 2 or 3 along the rod. They've all slid up in the right near the connection when you pull it out of the well. So if you see that, they're not doing their job for fatigue life anymore. So I would recommend the molded on ones, and not ones that are made for beam pumping applications. If they have straight fins on them, you don't want to be rotating a rod with straight fins on it. Straight fins are fine on the spin-through type couplings because you want it to stay stationary against the wall. But if it's going to rotate with the rod, like a molded-on guide, you'd like to have either something round on it, so either spiral or just a round body. But yes, reducing the spacing between the couplings goes a very long way towards reducing that effective curvature. And generally, even one guide will often be enough to solve a fatigue problem. Inspecting your used rods, like I said before, again, visual inspection doesn't find the cracks, but if you see something wrong in a visual inspection, you definitely want to get rid of it. But if you can do something like an eddy current testing or something like that can detect cracks, that would give you the best results. Corrosion inhibition, if you've got corrosion in your wells, if you're seeing corrosion pits on your rods when you pull them out, corrosion inhibition program will greatly improve your fatigue life as well. Some other things that you need to think a little more carefully about: pump size, rod diameter, rod grades. Some people think, I'll put a bigger pump in, so I'm going to have fewer cycles. True, you're going to have fewer cycles, but you're also going to have higher load in the rods, higher stress. What's the effect of that overall in run life? It's going to depend on the situation, and it will be different for some cases. Sometimes it's better, sometimes it's worse, so be careful with that. And the same thing with diameter. You think, I'm going to put a bigger diameter rod, it'll lower the stress. It lowers the mean stress, yes, but it increases the bending stress. So what's the effect of that? And again, it will depend on the situation. Sometimes it's better, sometimes it's worse. Rod grades, again, that depends on what's the shape of the SN curve for that rod. So if you can find the SN curves from your manufacturers, you can look at those and try and use that to help you select your materials. But if you're using software to do these calculations, don't expect perfect results. There's a lot of assumptions and simplifications that go into the software, and you have to give the software the SN curve for your material. That's probably not built in. It probably has some default curve. So you want to make sure you get the correct SN curve. But even if you don't have that, if you're using the default curve and you've got to deal with these assumptions and simplifications, the software is pretty good at giving predictions of whether something's going to increase or decrease your fatigue life, or it's going to give you a relative comparison between two designs to show this one's a lot better than this one, for example. So software can be useful for that, even if it doesn't tell you an exact lifetime that you're going to get. It can give you directionally accurate information. On the bright side, a lot of the things we do to reduce tubing wear also help us improve fatigue life. And in a lot of cases, the tubing wear is the bigger problem. You see a hole in the tubing before you see a broken rod. So you're going to do things to solve the tubing wear problem, and a lot of those things will help reduce fatigue as well. So for example, obviously smoother wells, continuous rod, smaller diameter couplings, using rod guides, all these things work for both wear and fatigue. I've got plastic line tubing up there. That one kind of depends on the mechanism. Some people have different opinions on how the plastic line tubing actually works. My feeling is that it works by the coupling wears into that plastic because it's a fairly thick plastic lining. So if it wears into that, even a few millimeters into that, that allows more of the rod body to be in contact with the tubing, reduces the contact load on the coupling, reduces the wear. But at the same time, it's essentially reducing the upset size. As that coupling wears into the plastic, it's as if the coupling is a smaller diameter in terms of the fatigue life calculations. So it's benefiting you there as well. If you're using a tubing rotators are great for reducing wear, probably give you 3 to 5 times the life of your tubing string. Has basically no effect at all on fatigue life. So you've solved your wear problem. Now maybe the fatigue problem is going to be what you see first. So it's a good idea, absolutely. If you got high tubing wear, you want to run a tubing rotator, but you do also need to think about your fatigue life as well. Snap-on rod guides. If a snap-on guide slides up to the coupling, it's still probably going to help wear. It's going to be spreading some of that load out a little bit, reducing the contact load on the coupling. But if you don't have the distance between them anymore, it's not going to be doing anything for your fatigue life. So you want to make sure you've got guides that are staying in position. Spin through centralizers. So I'm talking about the ones that go with the coupling. PCM sells these, other companies sell these. They're very, very effective at reducing wear. And they're also really good to use to prevent vibrations from the pump or the drive head from being transmitted through the rod string. So putting a couple near the pump, never right at the pump head, always at least 10 feet above the pump, but put one or two down near the pump and one or two up near surface can really actually be very good. Going through severe dog legs, again, they can really reduce that wear, because what they have is there's a plastic sleeve that stays stationary on the tubing wall, and the rod rotates inside that. So there's no rubbing contact on the tubing wall. So it's really good for that. Unfortunately, they're a larger diameter than a standard coupling, so that's increasing that curvature concentration. So it might end up making fatigue worse. So if you're going to use those, and certainly I think they are a good thing to use, you can either combine them with some rod guides, put one rod guide in the middle of the rod, and that will almost certainly eliminate any problems. Or if that's not an option for you, even just using a smaller diameter one. So if I've got 3.5-inch tubing, I don't need to centralize the rod inside that 3.5-inch tubing. I just want them to have a sleeve against the tubing wall. So I can use a centralizer that's made for 2 7/8. Maybe right at the top and the bottom where you're trying to stabilize vibrations, then you use the full-size ones. But through the dog leg, I can use a smaller one and reduce that upset a bit. I still get the effect of the wear reduction, but I'm going to reduce the fatigue problems. Okay. Just a couple of examples here. I mentioned in Canada they've been using continuous rod and these reduced upset rods for more than 25 years now. These technologies are really being shown to work at reducing tubing wear and fatigue failures. Unfortunately, I couldn't find any good papers that are published on that, but like I said, there's 25 years of experience there. It works. A couple of papers I did find, both from Columbia. The first one there is talking about standard rods, and they switched to continuous rod. So when they were running standard rods, they saw 53% of their rod failures were at the upset. So these are the fatigue failures. Another 42 were in the connection. So that's 95% of your failures come from one of those two things, which is what I expect, or perhaps even higher, because that's basically what's going to happen to your rods, is one of those two things. The connection failures, you have to look at that other webinar that I gave you the YouTube link earlier, or if you don't have that, you can go onto our website and go on the webinars page on our website, pcmals.com, and then you can find the links to the old webinars and the one on connection makeup, which is the first webinar we did. We'll talk about how to solve those 42% of the problems here. So when they use continuous rod, of course, they don't have connections anymore, and they don't have these rod fatigue failures, or nearly as many. The rod failure time to rod failure increased from less than 100 days to about 500 days. So pretty good improvement there. The next paper there is a more recent paper, and they're talking about this modified connection. So this is the 1 1/4-inch rods with a 1-inch pin, and they modified the pin a little bit to put some more threads on it to improve it for its torque strength. Those modified pins you do not want to use for a beam pump application, though. Adding those extra threads actually makes it worse for a beam pump, but it's very good for PCPs. But again, an 1 1/4 rod with a 1-inch pin, so they're getting good torque capacity, but a reduced coupling size. Out of the 6 test wells, they have increased run life in 5 of them. The 6th one had a tubing failure, not a rod failure. So again, showing these techniques can work. Just an example here, we wanted to show you that PCM, we have some failure analysis tools. We have this database that we have, a web accessible database where we can track our failures and help record them for the companies who are interested in that. So in this particular case, there's all the information about the well. They put pictures in of the torque anchor and the tag bar and the failure itself. They've added the pictures in. This particular fatigue failure here was I added in this graph from our PCM design software because we had the analysis for this well in there. And I've marked where the failure occurred, which is very close to the highest dog leg in the well. A little bit above it though, and you'll often see that because the tension in the well is higher closer to surface. So you'll often see the failures being a little bit closer to surface than where the highest dog legs are. Or if you see two dog legs where maybe there's a higher dog leg deep in the well, it'll be the shallower dog leg, even though it's not quite as severe. That's where the failure will often be because of that higher tension. And then, yeah, just there's my email address if you have questions after the fact or you want to contact me at any time later. And here's the 3 references. The first one is a paper I wrote a few years ago. It has, if you like math, it's got a lot of equations in it, but it gives the full procedure for how to estimate the fatigue life using that curvature upset, and then looking at the curvature concentration at the upsets, and then looking at how to go from mean and alternating stress to the stress you can use on your SN curve. And then the two papers there that I referenced there from Columbia are listed there as well. Okay, so I'm going to go through the question and answers here. We've got a few questions there now. Again, if you have a question, please go ahead and start typing it now, because by the time I get to the end of answering these questions, we'll probably have a 2 or 3 minute delay in there. So if you only type a question in there, I might have ended the presentation before I see your question. So if there's a question that you'd like to ask, please go ahead and ask it now. So the first question, it says, can you please elaborate more on the benefits of shot peening? Is it practiced on continuous rods? I don't believe that continuous rods are shot peened. I don't think that's done, but it will depend on the vendor. You'd have to double check with your vendors. The shot peening process is basically they take little pellets and they blast them at the rod. So it basically puts these tiny little indentations all over the surface. Those little compressive stresses there that for whatever reason, and I'm not a metallurgist, those things tend to decrease the likelihood of a fatigue crack from starting at those points. So it's something that's been done for the rods used in beam pumps for a very long time, and seems to work. I don't think it's on a continuous rod, but again, you'd want to check with your particular vendors. There's several vendors of continuous rod, and I can't say that none of them do it. Maybe there's some that do. Next question was, what sort of inspections do you recommend for used rods? I don't get much confidence from just a visual inspection of rods on this fatigue life. You're right. So the visual inspection, if you can see significant corrosion, if there's any corrosion pits are going to be the worst for fatigue, of course, because even if it's there's no fatigue crack already there, you put that back into a well, that's somewhere that a fatigue crack will initiate from. So any kind of corrosion, especially pitting, if you see a bent rod, should always be discarded, because that bent rod will have there'll be a significant curvature at that point. Or any other visible damage. You can see any nicks, any wrench marks, anything like that. Obviously, that rod should be thrown out. But even if a rod that's being used doesn't have any of those obvious damages on there still could be fatigue cracks. So there are techniques that can be used. The main one would be eddy current testing. And I know the manufacturers do this when they're making new rods, just to make sure there's no cracks in the material they've got from their raw material suppliers. So they will do this test before they make a rod. But I believe it's available. You can get that done at the well site as well. What it costs and is it available in your region, that's a different question, and you'd have to look into that. It may not be possible to do it in your areas if that equipment's not available, or it's too expensive. So then you have to make that decision of, do I rerun these rods, or do I run new rods? Some people, if there's rod inspection facilities available, they'll just send the rods out for inspection and run either new or inspected rods when they rerun their pump. And then those rods that are sent for inspection, if they're good, they can come back to the field and get used in a future well. Next question, are the chances of fatigue failure high just above the rotor due to the higher rod eccentricity? Certainly above the rotor, you do have that extra bit of bending there. So yes, there is a chance of having that problem there. It's very important. That's if you're going to run a centralizer above your pump, that it's at least 10 feet above there, above the pump. Because if you put a centralizer too close to the pump, you're really increasing that curvature that's required for the pump's eccentricity. As the pump rotor moves back and forth across the rod, you're causing more bending stress in that rod there. So keeping that centralizer at least 10 feet or even a full rod joint above the pump, very important. But beyond that, there's not much more you can do about that. And it's not actually, the pump eccentricity is not that high to really affect that. The curvature magnification from through the higher dog legs higher up in the well is generally more of a problem, because at the pump, hopefully you've got less than a 3-degree dog leg where you've landed the pump. So it's not a curvature induced thing, it's only that eccentricity. You're going to have more likely to have problems higher in the well where you've got more significant dog legs. And the last question that I see on here right now is, how feasible is it to inject downhole corrosion inhibitor, and is the only concern the compatibility with the elastomer? Well, that's a very good point. Obviously, any chemical you're putting into the well, you need to make sure it's compatible with your elastomer. And the different corrosion inhibitors, there are some that are quite good, and there's some that will be really nasty to your elastomers. So that's something to check on. And if you can provide a sample of your chemicals to your pump vendor, they should be able to do a test and see if that there's going to be a problem with that chemical. How feasible is it? It certainly, there are companies that do it. Depending on the product, that could be done through a capillary line. In some cases, it might just be poured down the annulus. I think a lot of the people on this call right now are in coal gas applications where there's a lot of gas coming up the annulus, so you might not be able to inject something down the annulus. So a capillary line then would get that fluid down to the pump intake. There are some companies that do batch injection versus continuous, just because it's easier to just dump a bunch down at once. Come in every few days and dump a bunch down. It doesn't work as well. Continuous injection is much better, because for some of these corrosion inhibitors anyway, the way they work is they form a film on the tubing surface, on the rod surface. And in a PCP application, of course, that film is going to get worn away very quickly. So you want to continuously replenish that. But in terms of concerns, yeah, it's just, you've got the extra equipment involved. You've got your chemical tank and pump at surface, your capillary line, if necessary, to get it down to the well. So the cost and difficulty of dealing with those parts, that's the only real concern beyond the compatibility with the elastomer.
Have you ever seen a fatigue failure which can be attributed to oscillating loads from slugs of sand or gas, or stick slip effects, lower frequency but potentially higher loads? Yeah, absolutely, that can happen. If you have slugs of anything coming through, gas or sand, changing those loads, so it's the same thing, it's a cyclic load. You're changing the torque, the axial load in the system. So absolutely, those will make fatigue worse. Generally, though, it's not a huge effect unless you're operating at really high stresses in your well. So if you're running your rods at 85% of the yield and you get a slug that takes it up to 95, and you have repeated slugs like that, that can certainly have a significant effect on your fatigue life. If you're running down at 20-30% of rated load, those slugs probably aren't going to do very much. Stick slip is perhaps a little more serious, because it can be significant effects, and it's generally more frequent. If you're having stick slip, that could be happening every few revolutions. So it could be, you're having those repeatedly, very high frequency. So that is that absolutely can lead to fatigue failures. Absolutely. Next question was, under which conditions would I recommend a hollow rod? Hollow rods are good. I've got nothing bad to say about hollow rods. Obviously, they're going to be more expensive than standard rods, so you have to decide if that's something that you're interested in. If you need to be able to pump a diluent down the well, I've seen people who are pumping them or using them to be able to pump hot water down. They've got a wax problem and they need to keep the temperature high, so they're pumping hot fluid down them. So things like that are really good, but also for wear and fatigue, because depending on which grade of the hollow rod you're buying, some of the grades have no upset at all. which means you've got none of this effective curvature effect. They just follow the curvature of the well. So that those can be really effective in those cases. They also have other advantages in terms of backspin. There's not as many twists in the rod, so you don't get as much backspin. For stick slip, again, there's less flexibility in the rods, so the drive system forces the pump to go through those stick slips with lower oscillations. So there can be a lot of good applications for hollow rod, and certainly fatigue failures is one of them, because again, you don't have the effective curvature effect of these at the connections because there's no upsets.
Okay, at this point, there doesn't look like there's any more questions, so I want to thank everybody for attending. This was number 7 in our webinar series. I don't know how many you might have seen in the past, but the previous 6 are all available on the website. And this one will be in a couple of weeks as well. It usually takes us a couple of weeks to get them on there. So if you've got colleagues you think should see this, you can let them know to check back on our website in a couple of weeks. This is a continuing series. We will be doing more webinars in the future. I don't have the topic for the next one yet, but I suspect it'll be in a couple of months, and we'll find a topic that should be of interest. So we'll let you know when that comes out. So again, thank you very much for your time today, and I hope to see you again at the next one. Thank you and goodbye.